Hi, my name is Wei Hu. I'm the Senior Vice President of Development, and I'm responsible for high availability technologies, including things like blockchain, crypto security, and so forth. Today, I'm going to share with you what's new with in-database blockchain and crypto security. And this will include features from the upcoming 23C database release. To start with, I want to explain why you need crypto secure data management. Today, we have a lot of security mechanisms built into the database and in the environment around us, but they're really focused on keeping criminals out. But what happens when criminals break in through your perimeter, right? Blockchain adds another layer of data security. It protects data from being illicitly modified or deleted, even if the criminals manage to break in, even if they manage to steal your passwords, break through encryption, break through firewalls, and so forth. The way this works is that blockchain uses cryptographic digests and signatures to implement crypto-secure data management. Blockchain is compelling but very difficult to implement. Okay. According to Deloitte's survey, blockchain stands as one of the top 5 strategic priorities. 93% of the respondents who deploy blockchain solutions says that it offers a compelling business case. So this is wonderful. However, blockchain projects also have a notoriously high failure rate. IDC says that the complexity and the costs connected to the creation and configuration of a blockchain and maintaining infrastructure are often seen as a barrier. To realize the potential of blockchain, it needs to be much easier to implement. And this is what we're about. We're about providing blockchain for the masses. At present, blockchain has mainly been used to develop decentralized multi-party applications. Blockchain requires new applications, new development methodologies, new data management products, and new business processes. And that's a lot of change. With Oracle Database 19c, we first released breakthrough technology that deeply integrates blockchain into the Oracle database. This makes it possible to implement blockchain in mainstream enterprise and government applications with minimal application changes. And it provides a full functionality of the world's leading database on crypto-protected data. Oracle Database 23c makes this technology even more powerful. The benefits of blockchain are now available beyond decentralized multi-party applications. The first goal of this technology is to prevent illicit changes to data. Oracle blockchain focuses on preventing illicit changes to data that records important actions, assets, entities, and documents. Things like contracts, titles, payment transfers, ledgers, account statements. These are examples of data that must be preserved and never modified. And this kind of data can only be deleted when it is obsolete. Illicit changes to important documents like this have dire consequences. You can lose your assets, you're exposed legally, you can lose your reputation, and so forth. A noteworthy point about Oracle crypto security is that it is not limited to providing changed ledgers like conventional blockchains. Oracle crypto security can also protect reference data as well. When we talk about data protection, we need to talk about vulnerabilities. Okay? There are 2 unavoidable problems with existing security techniques. The first unavoidable problem is hackers. Okay. What happens if a hacker finds a way to bypass your security mechanisms? And it's a sad reality that obscure new security breaches are discovered all the time. The second unavoidable vulnerability is really us, the human users, right? Users can be corrupted or even more likely compromised. Okay. An unauthorized user might use their valid credentials to make illicit data changes. This could be a rogue insider who are corrupt or malicious, administrators, developers, support staff, and so forth. Or more likely, it could be compromised users. A criminal impersonating an insider or an end user, using credentials stolen from the insider using malware or social phishing attacks. In the worst case, it could be a corrupt enterprise and government agencies, organizations that intentionally change records to steal assets or commit fraud. New security hacks are unavoidable. Okay? In 2020 alone, there were like 2,700 critical security vulnerabilities. Corrupt insiders are unavoidable. Okay. There's a story about this bank teller that stole over $1 million over 10 years by falsifying bank records. Stolen insider credentials are unavoidable. This just happened recently. A hacker pretending to be a corporate IT person persuaded an Uber worker to hand over a password that eventually allowed full access to Uber's source code, email, and other internal systems. Bribing of insiders is unavoidable. An employee was offered $500,000 to insert malware into Tesla systems. Now, to his credit, the employee reported the bribery attempt. So, given that all these things are unavoidable, what can we do to limit the damage? Okay. Although we can never eliminate these vulnerabilities, we can certainly work to limit the damage they cause. Blockchain will not prevent your data from being stolen, but it provides an additional layer of defense that can prevent the dire consequences of your data being changed. Think about this. What is worse? Someone seeing my bank account or someone stealing the money from my bank account? Oracle provides protection for many types of illicit changes. Oracle cryptosecurity technologies can be adopted incrementally to protect against the types of illicit changes that are most important for each use case. So for example, we have immutable tables to prevent illicit insider changes, blockchain tables to detect illicit hacker changes, distributed digests to detect authority-ordered illicit changes, and data signing to prevent impersonated data fraud. Out of these four types, only illicit changes related to end-user identity require significant application changes. Now, for simplicity, I sort of grouped these into four categories, but some of these mechanisms are also useful for protecting against other kinds of attacks. I want to start with preventing illicit changes by insiders using immutable tables. Oracle immutable tables prevent illicit modifications by insiders using a database like SQL. Okay. For example, a rogue employee whose credentials were stolen. An immutable table is a kind of table that allows new data to be added, but existing data cannot be changed or deleted by anyone using a database. That includes database administrators. Create an immutable table and insert only immutable table is very easy. You simply add the immutable keyword to the create table statement. Okay. And once you do this, this table can be used to store relational data or JSON or log documents. And these tables are not restricted to ledgers. You can also store reference data. An immutable table is like any other table, except that immutable table users cannot update rows, right? But you can insert new versions of a row. You cannot delete rows unless they've expired. You cannot rename columns, but you can add or drop columns. You cannot convert an immutable table to an updatable table or vice versa. And you cannot modify the table metadata in the dictionary to make it writable. And the great thing is that using immutable tables requires no application changes. It looks just like a table, and regular SQL works against it. Okay, so this is the first type. The next prevention is, how do you detect illicit changes made by hackers? And this is where cryptographic data chaining comes in. The threat we're worried about is that what if the database software that enforces immutability is bypassed? For example, by a hacker using a new security vulnerability, or by a rogue or compromised system administrator who uses operating system credentials to modify or bypass the database software. It's called insider hack. Blockchain detects changes to data by computing and safely storing a small cryptographic digest of the data. So the idea is if the data is changed, then the cryptographic digest of the changed data will no longer match the previous digest that you computed. This is how you can detect illicit changes. Even if the attacker takes full control of operating system database, because no level of privileges allow you to bypass the math and the lines cryptography. Because if you change the data, the cryptographic digest would be different. Okay, that is the way it works. And you can't get around that. Okay, that's how you can detect when data has changed. So here's where we introduce the blockchain table. An Oracle blockchain table is an immutable table that automatically changes new rows to existing rows cryptographically. So we basically add this column of the chains, right? And the way it creates it is very simple. Again, you just add the blockchain keyword to the table creation statement, and you get a blockchain table. In a blockchain table, newly inserted rows have a cryptographic digest computed that is based on the row's contents, right? So we computed cryptographic digest based on row's contents. Plus, we add in the crypto digest of the previous row. So that's how we chain things together. Okay. So any modification of data in the chain breaks the cryptographic chain. In this diagram here, if someone later comes in, a hacker comes in and modifies, row number 2 there, right? The crypto digest row 2 itself would not match as well. And furthermore, all the rows that come after row 2, their crypto digest will also break because it's computed on the old contents. Okay. This is how we can detect when you modify rows in the chain. Chains can be verified by users with a built-in procedure to verify the rows in a blockchain table. But in addition, the chains can be independently validated without depending on the database. Okay? This is the case if you don't trust database software. We provide an open source library that is running outside the database to read the chain data and verify the crypto digest. What this lets you do is to have an independent data auditor who can validate the data for you. This is sort of like a financial auditor who validates accounting records for companies. Okay? And this relieves end users from having to do this. And furthermore, it actually protects data privacy because then only the auditor needs to see the data on all the users to validate the chain. As you might expect for the Oracle feature, blockchain tables are extremely scalable and available. Blockchain tables are very fast. The response time of the insert can be sub-millisecond, and that includes the commit. In Database 23C, we further improve performance. We reduce commit latency by computing the crypto hash incrementally, and we speed up the removal of obsolete rows using partition drop. It's extremely scalable and available using Oracle RAC scale-out clusters, and we use DataGuard for geographic disaster protection. It's easy to use. Okay. Immutable tables and blockchain tables are Oracle converged database features. So that means you can use them as part of your regular database with all your other data types. And you don't have to use a blockchain-only database like Amazon's Quantum Ledger database. These tables require no application changes. They're accessed with standard declarative SQL. Okay. It supports the full analytic and transactions on table data. And starting with 23C, it also supports distributed transactions, or XA. And best of all, it's a free feature of all the Oracle database editions and has been available since 19C release 10, 19.10 release. Okay, and that came out January of last year. Now I want to go into some of the enhancements that were built into the Database 23C release. The first one is concept of row versions. Now, the way that immutable and blockchain tables work, you cannot update existing rows. Therefore, when you have new data, you always have to add a new row. Okay, so a blockchain table will tend to have multiple versions of the same row. For example, if I keep a record of the cars, each time the car changes owners, I have to add a new row. Okay. So in 23C, we automatically track the latest version of each logical row. When you create a blockchain table, you can specify up to 3 user columns whose values specify the rows that are logically the same. In the example I have with cars, I may have a car ID column that stores the VINs related to the car, right? So for every given car with this VIN number, you actually group all those rows together. And then there is a system-generated view called car registry last dollar in this case, that will just contain the last row for each row group. Okay? So this is a way you can quickly find out the last owner or the current owner of this car. Because if you have a record for each time the car gets sold, you have to scan through lots of records to find the current one. Well, this is a very quick way to just find the current or the latest version of that row. This is the benefits, of course. It's very easy and fast. Okay, the database tracks the last row, so you don't have to scan the table to find the most current version. And it's fast because we know where the last row is, we can directly fetch it. So this is done by just adding the row version keyword, specifying the columns whose values specify which rows logically belong together. Row versions work with blockchain tables as well as immutable tables. With blockchain tables, we also have this thing called user-specified chains. Earlier, I talked about how you can verify the integrity of the crypto hash chains. Now, to do this for the entire table means you got to read all the rows. This is not good if the table contains data from multiple customers, because I don't want a customer to read the data for every other customer. To address this, the database 23C release supports separate chains for each user-specified grouping of rows. So you can specify the rows that belong to the same chain using, again, values of the up to 3 columns. So in this case, I can just say that, gee, group all the rows belonging to the user Sam Jones and with his account number. Okay? So group them all together into a single dedicated chain. Okay? So what happens is we'll create separate chains for each customer account number combination. Then when you verify the integrity of this blockchain, you only have to access the rows that are part of this chain. So this user, this customer, will only see his own data, right? And you only need to see his own data to validate his own chain. The benefits are, first of all, it's faster validation, because you don't have to scan through everybody's data. And more importantly, you don't have to expose all the table data to the verifier, just the data that belongs to this single entity. And you specify this by basically, in the create table statement, add the end user chain and specify how you want to classify the user chains. Another new feature in 23C is creating crypto-secure change log for all your data. Immutable and blockchain tables are great for insert-only data, but sometimes you have tables where the data can be updated or deleted, right? So how do you audit these tables? This is where the combination with the flashback time travel feature comes in handy. Flashback time travel tracks changes to tables and stores them in a log history table. And this actually is very useful for compliance with record stage policies and audit reports. And once the data is stored in flashback time travel, you can actually use SQL to access historical data. You can run SQL queries against data, say, let's say, 6 months ago, so forth. So you can combine crypto-secure blockchain table and use that for flashback time travel. What you do is you protect the flashback time travel change logs, against tampering by making them blockchain tables. Then what you get essentially is a tamper-resistant history of changes to your non-blockchain table. So this gives you crypto-secure data protection to all your data, including data that is not in blockchain tables. There's some additional enhancements to blockchain tables in 23C. They can be replicated using Golden Gate and logical standby. We added DDL to add and drop columns to an existing blockchain table. Basically, what this does is newer versions will see the newer or drop columns, and then the older versions, of course, preserve their contents. There's additional DML to create blockchain table or select, and so forth. And these functions are also supported for immutable tables. All right, so now that I've sort of talked about protection against tampering by hackers, I want to talk about the next threat, which is detecting cover-up of illicit changes by authorities. And this is where the other feature of distributed publication of data digest comes in. Detecting the cryptographic chaining of rows that I described earlier can be defeated by a large-scale cover-up, right? What if, for instance, you change the rows and then rewrite the entire chain from the very first record down to the last? Then the entire chain will be consistent, and you can't tell that something has been done. Okay, so this is really a massive cover-up. Now, some example where this can happen is, for the example, an order can be given by a corrupt executive or government authority to replace the entire database. Or a sophisticated cybercrime organization deletes and rewrites the entire database. To prevent this case, to detect the cover-up, Oracle enables the cryptographic digest of a table to be distributed publicly. So the idea is that when you insert a row and you compute and you get a cryptographic digest back, you send it out. Okay. And so the way this works again is the digest includes all the table chains or select a set of rows. And the table chain, the digest, is computed on the contents of the row, the user data as well as metadata and so forth, right? And then the digest is computed, is cryptographically signed by the schema owner to ensure it cannot later claim to be fake. So essentially, the database will return a crypto digest, and it will sign this crypto digest using a public signature. And signing it means it cannot be repudiated. So later you cannot claim not to have sent this data out. Then once you get the signed digest, you can distribute it periodically, like once a minute, or whenever important data is inserted. When you insert important data, you can immediately send out the signed digest. The signed digest is safe. The digest is computed from the data, but you cannot go backwards. You cannot take the digest and recompute the original data. Therefore, since the digest cannot be used to infer the actual data, it is safe to distribute it anywhere. You can post these signed digests to an independent public store like Facebook, for example, or a public blockchain, or you can send it by email or via REST call. So you can basically distribute it widely to independent storage locations. And when you do this, this helps you detect cover-ups, because basically when a cover-up has happened, the digests of the new rows will be different from the previously published digests. So someone may change the entire database, but it is very difficult to change the entire database, plus copies of the digest in Facebook, in Twitter, and so forth. And so distributing digests publicly across multiple independent services prevents an authority or cyber attacker from being able to delete all the independent copies. And this technique of heterogeneous distribution provides much stronger protection than a homogeneous distributed blockchain. And the best part is that publishing a data digest does not require changes to existing applications, because it is done on the side. Now, verifying these digests can be done independently. The blockchain table uses a documented hash file algorithm and platform-neutral representation of the raw data. Okay. So we've published samples in GitHub showing you how to basically read the data, verify it, and export it. And it supports 3 different modes, right? You can do it one time, you can do it continuously in a loop, you can publish the digest into an external blockchain table, blockchain platform, in our case, the Oracle blockchain platform, and so forth. All right, so the last thread that I want to talk about is data falsification by impersonators. And this is where the third technique comes in, with end-user data signing. The situation we want to prevent is following. Suppose new data is inserted falsely in an end user's name. I take someone else's identity and add a record there. Okay. So for example, an insider can impersonate another end user, or an end user's credentials are stolen by a hacker, or a developer operator hacker bypasses the application's credentials checking. Okay. Any of these cases can cause a record to be falsely inserted in the database using somebody else's name. To address this vulnerability, Oracle allows the end users to cryptographically sign new data that they insert. So by signing the data, we sort of prove that, yes, I am the person who actually put this data in the database. Now, this does require the users to have a digital identity and public certificate. Okay. So this tends to be more common for businesses than for consumer end users. Okay. It also requires that applications implement digital signing of data. The way this works is following. When you insert a row, the end user signs the data using a private key, and that private key is never passed to the database. The end user then registers a digital certificate that contains a public key to allow the database to validate the signatures on the data. And then we store the signatures and the certificates in every single row. So this allows somebody to come later and verify indeed that, yes, this was signed by the person. In 23C, sorry, let me back up. So this basically allows you to verify that, yes, I am the person who inserted this row. 23C, we made it more flexible. First, we support delegated signers. In 19C, the row can only be signed by the user who inserted the row. But there are cases where a row needs to be signed in addition to. So for example, you want 2 people to sign the row, right? Or as an alternative, like I may delegate somebody else to sign on my behalf. So 23C supports what's called a delegated signer, which stores the delegate certificate in dictionary table, right? Then the way it works is the table owner, instead of signing directly, I can grant the sign privilege to somebody else and allow somebody else to sign using their own signature, the rows. And you can further restrict who can sign by specifying the user IDs and the row insert. But basically, these are just ways to allow somebody else, an additional signer, or instead of signer, to sign the rows. And we also make it easy to specify the exact row to be signed. In 19C, you have to specify the instance ID, chain ID, and sequence number. In 23C, there's new API that allows a row to be uniquely identified by up to 3 user column values. Right? So in this case, you just say, I want to sign the row where the ID is 2 and the user is caret, for example, instead of specifying the instance ID, chain ID, and sequence number. In 23C, we also introduced the concept of a end-to-end crypto receipt or a counter signature. The database, when it gets new data, can actually countersign the new data to allow the user to ensure that the data was received by the database. Okay? And this is why we call it an end-to-end crypto receipt. And the goal of this is to defend against what's called the man-in-the-middle attack, whereby a middle tier takes the user data and sort of like throws it away, such that it never made it to the database. So by providing a crypto receipt, the database basically gives you a certificate signed saying that, yes, I guarantee I actually got the data. And so this way, the application can know that, yes, my data was safely received and recorded by the database. We essentially, this is essentially a counter signature by the database and a new procedure to sign the rows. This new procedure provides that we allow the application to sign the row and ask the database to return the counter signature. And so once you get the counter signature, you can actually store somewhere else for future validation. So this actually, I think, is a very, very good end-to-end security mechanism, the end-to-end crypto receipt. I want to start wrapping up by comparing the blockchain table with what I call conventional peer-to-peer blockchains. A blockchain table with a publicly distributed signed digest is simple to use and provides most of the benefits of full peer-to-peer blockchain products. Blockchain tables prevent illicit changes made using the database and detects illicit changes that bypass the database. Now, if you want to directly prevent all forms of illicit changes, right? Sorry, let me back up. If you want to being able to directly prevent all forms of illicit changes does provide strong protection. And, however, we believe that if you can detect illicit changes, it also indirectly prevents most fraud. And that's because a criminal won't commit fraud if they know they will be caught. For example, a criminal won't take a bribe while they are being video recorded. Now, if you want to directly prevent all illicit changes that bypass the database, that really requires a peer-to-peer blockchain architecture with consensus-based multi-party agreement for every change. So if we can make a change, somebody else has to agree with the change. Okay? And this is where the peer-to-peer comes in. Peer-to-peer consensus does prevent the takeover of a single database from compromising their entire system. Okay? However, should be pointed out that peer-to-peer is still vulnerable to a common bug across all the peers. Peer-to-peer sounds good, except that peer-to-peer consensus requires new application development methodologies, and consensus requires major changes to business processes, which is much harder than technology, and how businesses interact with customers and partners. And furthermore, consensus requires sacrificing autonomy and privacy, because you can no longer make the change by yourself. You have to get some other party to agree to your change, and you have to expose data for that. Overall, peer-to-peer blockchains provide very effective illicit change prevention, but at the expense of significant complexity and trade-offs for mainstream use cases. And that is why we focus so much upon using this blockchain table model to avoid having to use peer-to-peer models. So use blockchain table with distribution of the signed certificates, of the signed digests. Use cases for blockchain and Oracle database. Because Oracle makes it so easy to adopt blockchain technology, it is now usable in every industry and in majority applications. Financial data, accounting, assets, payments, insurance. Logistics data, distribution, supply chain, shipments, recalls. Education, degrees, diplomas, and so forth. government data, legal data, trial data, taxes, permits, citizenship, titles, and so forth. And finally, corporate data, invoices, payments, contracts, employee records, intellectual property. We have many customer examples, but I thought I'd just pick one example to talk in greater detail. And this is the Luxembourg cashback wallets. Right? So basically, this organization, the Luxembourg government, have imagined this project to allow customers to support their merchants, right? So that they allow people to buy vouchers for various stores to help protect the businesses financially. And so the problem is that it's a cashback program, right, that requires shoppers' accounts to be maintained, to be protected, because the wallets contain balances of these vouchers, right? So you'll make sure it's tamper-proof and it can be audited by the municipality as well as the funding companies. The way the blockchain tables help you is that these accounts and wallets are tracked using blockchain tables, right? And periodically they publish the signed digests so that the auditors can check and verify against their own records to make sure that the data has not been hacked and tampered with. So the benefits are, this allows you to implement the cashback service using existing Oracle database without the extra cost and effort to introduce other technologies. So I think this is a very good use case showing how easy it is to adopt this technology to solve a real world problem of protecting your data against tampering. Blockchain is part of the Oracle Converged database. The Oracle Converged database supports any structured data, relational, graph, Avro, Parquet, blockchain. And it supports any semi-structured data, geospatial, JSON, XML, text. Converged supports all modern data. Converged database, by supporting all the modern data, it really simplifies application development and eliminates data and application fragmentation. And furthermore, this is best of breed for all data types. For example, Oracle supports better JSON than MongoDB, supports faster graph than Neo4j. And furthermore, by converging all these data types to a single database, we provide the unique ability for transactions and queries to span any data. So I can write a query that reads relational data as well as graph data, and is also stored in a blockchain table. And this further drastically simplifies development. Blockchain in the Oracle database addresses real-world data protection challenges. Immutable tables prevent illicit insider changes. Blockchain tables detects illicit hacker changes. The distributed digest detects authority order illicit changes. And finally, the data signing prevents impersonated data fraud. Blockchain is a free feature of the Oracle Converged database. It can be deployed incrementally with minimal app changes. I invite you to learn more about blockchain. There's a blog that we published, there's a hands-on lab, there's documentation, and of course there are additional sessions and open world issues to listen to about Converged database. And in addition, you can freely try our capabilities using our Oracle Cloud free tier. With that, I want to thank you for listening, and I hope you have a good time. Thanks.